All right, so before we start exercise 22, I want to talk about an actual application that we have for Taylor series instead of just looking at it theoretically. So let's say that you need to calculate the sine of 0.2 and you don't have your TI 84 plus calculator. Maybe you don't have a calculator at all. Maybe you just have an old-fashioned calculator that just does subtraction and addition and multiplication and division. Well, if you needed to find this answer and you don't have a sine button on your calculator, now you've got a different way to find it because we know what the Taylor, or in this case Maclaurin series, is going to be for sine of x. So we know that the sine of x is equal to, or approximated by, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and then of course we can go on and put in higher order terms. Well, if we actually wanted to find this, we could say that the sine of 0.2 was equal to 0.2 minus 0.2 cubed over 3 factorial. Now I could use higher order terms, but this might be good enough. So if I was going to do this, I would know that it would be 0.2 minus, and it's 0.2 cubed, which is going to be 0.008, and 3 factorial, which is 6. Now, maybe you have that simplified calculator so that you could do 0.008 divided by 6, or in the worst case scenario, that is actually long division that you could do yourself, but it's equal to about 0.0013. And when we do that subtraction, we get 0.1987. So if you wanted to compare this with what you would get if you plugged sine of 0.2 into your TI-84 plus calculator, being in radian mode, of course, we would end up with the sine of 0.2 is equal to 0.1986. So really, to 4 decimal points, it would be 0.1987, and those answers would be indistinguishable. Now remember, we talked about how you cannot assume that an approximation is going to work when you get farther away from x equals a. So in this case, we're using the Maclaurin series, so x is equal to 0. And as we get farther and farther away from 0, the approximation probably isn't going to work as well. But this is good to know. So let's go on to the problem. So exercise 22 reads, let f be a function that has derivatives of all orders for all real numbers, and assume that f of 0 is equal to 4, f prime of 0 is equal to 5, f double prime of 0 is equal to -8, and f triple prime of 0 is equal to 6. And part A says, write the third order Taylor polynomial for f at x equals 0 and use it to approximate f of 0.2. So this is what we were talking about. So we need to start by reminding ourselves what the Taylor polynomial expression is, and I've already written it over here. So Pn of x is equal to the summation from x equals 0 to n of the kth derivative of f evaluated at 0 divided by k factorial times x to the k. And in this case, we want to use n equals 3 because we want to do the third order Taylor polynomial. So let's just write out the terms over here. So P3 of x is going to be equal to f of 0 plus f prime evaluated at 0 over 1 factorial times x plus f double prime at 0 over 2 factorial times x squared. And our last term is going to be f triple prime at 0 over 3 factorial times x cubed. And then we already have all of these values for f and its derivatives evaluated at 0. So we can really just substitute in. So f of 0 is going to be 4. F prime at 0 is going to be 5 times x. F double prime at 0 is going to be negative 8 over 2 times x squared. And f triple prime is going to be 6 over 3 factorial, which is also equal to 6 times x cubed. Now we can clean this up a little bit. So we can say that P3 of x is going to be equal to 4 plus 5x minus 4x squared plus x cubed. And then if we want to use this to approximate f of 0.2, then we're just going to substitute in 0.2 everywhere that we see x. And this you can plug into your calculator, and you're going to get 4.848. Now this problem goes on, and it has a part B. And part B says, write the second order Taylor polynomial for f prime, the derivative of f, at x equals 0, and use it to approximate f prime of 0.2. So I'm going to need a different Taylor polynomial here. So I'm going to have P2 of x. And now I'm going to have to shift all of my derivatives, because the first term of a Taylor polynomial is the original function, which in this case is f prime evaluated at 0. The second term is the derivative of that original function, which in this case is going to be f double prime at 0 divided by 1 factorial times x. And the third term, or the n equals 2 term, is going to be the next derivative, or the second derivative of my original function, which is going to be the third derivative evaluated at 0 over 2 factorial times x squared. And I can substitute in my values here. So this is going to give me 5 minus 8x plus 6 over 2, because that's what 2 factorial is, times x squared. And again, I can simplify this a little bit. So I'm going to have 5 minus 8x plus 3x squared. And just as a quick aside here, what we're basically doing is taking the derivative of the third order polynomial. So what we're saying is that P2 of x is equal to P3 prime of x. So if we flip back here for just a minute, if we took the derivative of this, would we get what we have on the next page? And the answer is yes. So now what we want to do is approximate f prime of 0.2. And so I'm just going to substitute in 0.2 for all of my x's. So we're going to have 5 minus 8 times 0.2 plus 3 times 0.2 squared. And this is going to give us 3.52.